This video is going to look at nuclear physics. All right, let's first start with the symbols. These might be somewhat familiar from chemistry. Okay, you're going to have some sort of element, and then you're going to have the atomic number, or excuse me, the atomic mass and the atomic number. Okay, so for example, sodium has 10 protons, so the atomic number is 10. Now, it has 10 protons and 13 neutrons. So it has a total atomic mass of 23. So that's the number that goes on top. Okay, atomic number, A, number of protons, Z, atomic mass, protons plus neutrons, also known as nucleons, the things located in the nucleus. All right, physics, we love conservation. We have another conservation here, conservation of mass and conservation of charge. Both sides of the reaction must have the same mass and the same charge, which basically means that your atomic numbers, A, must be the same on both sides, and your atomic mass, Z, must be the same on both sides. So for this symbol down here, or for this reaction down here, the arrow is your breaking off point. So on one side, you have, let's look at A first. So we're going to look at the bottom numbers. We have a 92, X, and a 2. Okay, so 92 is going to equal X plus 2. So X must equal 90. Now for Z on top, I have 238 is equal to 234, that's the product, plus Y. So Y in this case would have to equal 4. Okay, nothing too tricky. Just make sure the left side equals the right side. Again, keep in mind there could be negatives. Okay, so if let's say I had a side, one reaction side had a 92, and this one had X and 93, X would have to equal -1. For example, that what happens when you have charges like electrons. All right, nuclear reactions. Nuclear reactions occur naturally if they release energy. Okay, nuclear reactions are happening all the time. Nuclear reactions are like chemical reactions, except that the nucleus itself is changing. So for regular chemical reactions, like what you learn about chemistry, the nucleus stays the same. Carbon is carbon is carbon is carbon. Now, carbon, it may not be carbon anymore. Okay, small atoms want to get bigger, and they tend to undergo fusion and beta decay. Larger atoms want to get smaller, and they undergo fission and alpha decay. So these are making their things smaller, these are making them larger. So let's take a look at those. Fusion and beta decay. Hydrogen and hydrogen, they have 1 and 1, they're very small. Okay, they want to get bigger. So they go through fusion and fuse together. Fusion, you fuse together and become bigger. And you end up with an anti-beta particle left over. Okay, beta decay, a beta particle is an electron. So what you do is you get a big atom. Okay, so a 6 and a 14, well, kind of small. And it becomes 7 to 14. So it actually becomes bigger. You increase the number of protons because you emitted an electron. Okay, so those are things getting bigger. If you notice, either the top number or the bottom number got bigger. Now fission has big guys fizzling apart. You know, it goes fizzle, fizzle, fizzle. So I have this big uranium-235, and it gets hit with a neutron. And he's going to split apart. You're going to get this guy and this guy, both of them are smaller. Okay? You end up with some extra neutrons and some extra energy as well. Fission breaks apart, fizzles apart. Alpha decay, alpha particles are helium particles. They have 2 protons and 2 neutrons, and basically along the lines of he's giving off a piece of himself. So this uranium-238 is cutting his hair, and he's losing 2 protons and 2 neutrons to become helium, I believe. All right, so those were the types of decay or nuclear reactions that happen. You saw me use alpha particles. The alpha particles are helium nucleuses, 2 protons, 2 neutrons. Betas are electrons. And the other thing that could happen is, well, there's another type of decay, which is gamma decay. And basically it's just giving off energy. And the term, or the symbol is that fun little gamma. Ooh, gamma decay. That should look like that. Symbol did not transfer. Okay, so physics. We know certain things. Modern physics. Ooh, let's find the problems. We know that like charges repel. We know this. We've seen it. It happens. However, the nucleus is made up of protons, positive, and neutrons, neutral. So there's nothing negative attracting the nucleus part. It's actually repelling itself. So why doesn't the nucleus fall apart? What is it? There's actually another force that we have named the strong force. And the strong force acts over teeny tiny distances. So, you know, a balloon, two balloons charged the same? No, not close enough. Really little teeny tiny difference. And it's stronger than the repulsion from the like charges of the protons. Okay, now, where does this force come from? Does it just appear? This is because of binding energy. So it takes a certain amount of energy to hold that nucleus together. That force takes energy. And that energy is known as the binding energy. Okay, so small amounts of mass are actually converted into energy. Einstein's theory. So we've all seen E equals mc squared. And we're like, that's a great equation. Very few people actually know what that means. E equals mc squared is basically telling you how much energy you get from converting mass into energy. All right, C is the constant speed of light, 3 times 10 to the 8th. M is your mass in kilograms. And E is your energy in joules. Okay, so why is that important? How would I use that? Well, let's first look at atomic mass units. Now, atomic mass units are like the moles of mass. And you've seen them a little bit in chemistry last year. You probably don't remember. Okay, for example, carbon on the reference table has the mass of 12.011, I believe, or somewhere around that. Okay. In atomic mass units, one atom has that mass. The reason why you guys explored moles in chemistry is because 1 mole of that atom is 12.011 kilograms. Okay, so that basically, moles got you into a mass that you can handle and deal with. Because atomic mass units are very small, but fairly easy to go in between. 1 atomic mass unit is 1.66 times 10 to the negative 27th kilograms. So if you're going from U into kg, you multiply. If you're going from kg into U, you divide. All right. Now, standard protons have these atomic mass units, and we deal in these because this is a heck of a lot prettier than dealing with tiny numbers like that. Okay, 12U has a lot easier to play with than 1.99 times 10 to the negative 26. Okay. So, here's an example. I want to determine the binding energy, so how much energy is needed to hold a alpha particle together. Binding energy needed to bind it. Okay. I know I've weighed, or mass, an alpha particle, and it actually has a mass of 4.00151 U, atomic mass unit. Okay. Well, an alpha particle has 2 protons and 2 neutrons, giving you 4 total nucleons. Okay. Now, every proton has a mass of 1.00 times 10 to the 27th. And if I have 2 protons, then I multiply that 2 by that number to find the mass of protons. Okay. You know, if you have 2 people and you add their masses together, you have 2 protons, you add their mass together. You do the same thing for the 2 neutrons. All right. So those are that's the mass of the 2 protons and the mass of the 2 neutrons. If you add them together, you get the total mass of 2 protons and 2 neutrons in atomic mass units. Okay. That's how much 2 protons and 2 neutrons weigh. Alpha particles have 2 protons and 2 neutrons. However, it does not weigh that. That difference is your binding energy. So what you do is you take what it should weigh and subtract it from what it actually does weigh. And you get the difference in mass. So this is the amount of mass that has been converted into energy. Woo! Mass to energy. Just think about it. It's so much fun. You'll have a question where you changed my dog into energy. Sorry, doggy, but you can power my house for a long time. All right. So that's my binding mass in atomic mass units. But if we're dealing in energy, we want kilograms. So we take this number and we multiply it by our conversion factor, which was 1.66 times 10 to the negative 27. So that number times 1.66 times 10 to the negative 27 is equal to that. So that's our answer in kilograms. Now binding energy, E equals mc squared. I know how much mass was converted into energy, and how much energy did I get from that mass? Okay, because we want to know that. So I take my mass, and I multiply it by c squared. 3 times 10 to the 8th squared. And I get my energy in joules, which is 4.53 times 10 to the negative 12 joules of energy. So my steps, find the mass of pieces, subtract it from the actual mass to find your binding energy. Take that binding energy, convert it into kilograms, and then use E equals mc squared to find your energy in joules. This is just a fun chart for you to look at. Okay, average binding energy for nucleon. Okay, as you can see, starts very low, 0, and then gets bigger and bigger and bigger, and eventually it starts to get smaller. As you end up getting in the big ones, the amount of energy you need to bind it together is quite a bit smaller. This is an interesting point to notice. The last thing for nuclear physics is half-life. Half-life is exactly what it sounds like. It's the time it takes to lose half of whatever you have for it to decay. So if I have carbon-14 decaying into carbon-12, okay, that basically means it's giving up 2 neutrons every time it decays. All right. If I start with 16 carbon-14s, every half-life I'm going to lose half. So in one half-life, I will lose half of it. Okay, so I'm going to have 8 left over. The next half-life, I'm going to lose another half, and I'll have 4 left over, etc., etc., etc. Half-life changes depending on the type of material, and it can be anywhere from darn near instantaneous to thousands and tens of thousands of years. And we use that a lot in carbon dating for like dinosaur bones and things like that, because it doesn't change. A half-life for a certain material is always constant. A nice equation for it is the remaining is equal to the original times 1/2 t, and t is the number of half-lives, not the total time, the number of half-lives. Okay. So that's just basically a way to throw it into an equation. You can usually do it in your head too, as long as we stick out with consistent half-lives. For example, if I have 100 grams of carbon-14 and experiences 3 half-lives, how much is left? Half-life number 1 leaves me with 50. Half-life number 2 leaves me with 25. And half-life number 3 leaves me with 12.5. 12.5, not 1.25. Okay, that's it using without the equation. If I wanted to use the equation, I would say, okay, I'm solving for how much I have left. I started with 100 times 1/2 to the third. So that is equal to 100 times 1/8, which is 12.5. Both work out the same. Now, if the 100 kilograms of carbon had already experienced 2 half-lives, so that's what I have remaining after 2 half-lives. I had 100 grams remaining after 2 half-lives. How many did it have initially? Okay, well, 100. If I go backwards, then before that second half-life, I had 200. And then I go back to 400. So I started with 400 kilograms of carbon, and I experienced 2 half-lives and had 100. The way to do it in the equation would be I have 100 remaining. I'm solving for my original. I'm just going to make a fun fancy O. 1 half times 2. So that's 100 equals O times 1/4. Okay, which is the same thing as 100 equals O over 4. Multiply both sides by 4. 400 is my original amount. So, do whatever way makes you happy. That's it for the lesson. Good luck on your homework.